us come back here. So alpha t is this. Now you know that alpha w I can write as CL by CL alpha wing plus alpha naught. How? Please give a thought to this. It should not be so difficult. Yes or no? Okay, let's see. CL is equal to CL naught plus CL alpha into alpha, or I can write this as CL alpha into alpha minus alpha naught. That is, if you see, if this is the CL and this is the alpha, so this is CL naught. One way to write is this, another is this is alpha naught. What is alpha naught? It is basically a negative angle. At alpha naught, CL is 0. So I can write CL also in this fashion. You can see at alpha equal to alpha naught, CL is 0. Alpha equal to alpha naught, CL is 0. And you could see from here that CL at any alpha I can find out. Okay? If at alpha equal to alpha naught, you could see CL will become 0. And typically alpha naught value is negative. That is very important. You should understand alpha naught is negative. So I can use this expression here and write here using this expression alpha w, here I put alpha w equal to CL by CL alpha wing plus alpha naught. Is this clear? Once I do that, now I will substitute that expression here. Okay? So let me write it here. So then I get alpha t equal to alpha naught plus CL by CL alpha wing 1 minus d epsilon by d alpha minus IW plus IT. What I have done? Alpha naught, alpha t equal to alpha w, and alpha w is CL by CL alpha wing plus alpha naught. So I have written it like this, where the expression was alpha w into 1 minus d epsilon by d alpha. 1 minus d epsilon by d alpha is here. For alpha wing, I have put this expression, CL by CL alpha wing plus alpha naught. Then I have got IW, and then also I should not forget about minus epsilon naught. Now see whether we have taken care of everything or not. This part we have taken care. This part minus and plus, this have been taken care, and epsilon naught we forgot to take, it is here. Right? Now if I expand, you could see here this alpha naught into d epsilon by d alpha is nothing but epsilon naught. But since alpha naught is negative, so this and this term will go after multiplication. So I get alpha t equal to alpha naught plus CL by CL alpha wing 1 minus d epsilon by d alpha, right, minus IW plus IT. This is the expression. Okay? This you see alpha naught into minus d epsilon by d alpha. And since alpha naught is negative, and you know this into this is nothing but epsilon naught, so this and this will get cancelled. So this term will disappear. So you will get a neat expression of alpha tail in this fashion. Okay? Let me erase this. A lot of expressions are waiting. I repeat again, don't get disturbed by these expressions. Anywhere if you have a doubt, put in the blog, in the open forum. We are there to help you out, right? These are very straightforward things. It looks clumsy. And I also personally feel very uncomfortable, if I tell you honestly speaking. Let me erase everything now here. So we are now here Fs equal to minus G AC CE half rho V square neta T. This is nothing but Q into CH. So for CH we'll write CH naught plus CH alpha into alpha tail. Already alpha T expression we have derived. So let me write here, it is alpha naught plus CL by CL alpha wing to 1 minus d epsilon by d alpha minus IW plus IT. So this is this. Then you have CH delta. And what is that delta required? We know delta required will be always dictated by delta E equal to delta E naught plus d delta E by dCl into Cl trim, and d delta E by dCl will come from dCm by dCl fix. So, we will write it as delta E naught minus dCm by dCl fix into Cl trim divided by Cm delta E. This expression you know that delta E equal to delta E naught plus d delta E by dCl trim into Cl trim. This you know. So, that is the same thing I have put here, and now we have to put the other term, that is Ch delta T into delta T because of tab. This completes the huge expression which was waiting to come on the blackboard. It has come. It doesn't look that ugly. If you could see that, this is already we have derived alpha t just now. This we have been using for long, and this tab we have also discussed today. Now what? Make it simplified. So, we write it as Fs equal to k. Wait a minute, I will explain you what is k. A also is coming here, Ch alpha Cl by Cl alpha wing to 1 minus d epsilon by d alpha minus Ch delta into dCm by dCl fix into Cl by Cm delta E plus Ch delta T into delta T. This is the expression. Then question comes, what is K and what is A? This K is minus G AC C neta T, and A is another big expression. This is all Ch naught plus Ch alpha into alpha naught minus IW plus IT plus Ch delta into delta E naught. Where from these things are coming, you could see here that Ch naught into delta E naught, that has been taken out. Okay. Similarly, Ch alpha into alpha naught minus IW plus IT has been taken. So, this if you sit with a pen and pencil with a piece of paper, you should be able to do this, nothing. These are all big expression. Let us try to get feel out of this expression. Right. Now, I leave exercise to you. I am sure you will be able to do it. So, I erased all these things now. We have already done today dCm by dCl free equal to dCm by dCl fix, right, plus Cl alpha t by Cl alpha wing Vh neta t to 1 minus d epsilon by d alpha tau into Ch alpha t by Ch delta E. Okay, this we have done it, and we realize that this is destabilizing, and many books this will be saying dCm by dCl, okay, control free, which is destabilizing for a configuration where hinge line is ahead of the central pressure over the elevator. This also you need to use Vh equal to or Cm delta E equal to minus Vh neta Cl alpha t into tau. This also you know. Use this into this to show that now I can write Fs is equal to k half rho v square. This is like this. Then A plus Ch delta t into delta t minus dCm by dCl free. Now it is coming free into Ch delta by Cm delta into Cl. I am sure smart enough to do this. Anyway, we will be giving these expressions or derivations in our open forum, but I am sure it doesn't take much time to use this and get that expression, right? You are all engineering students. Let us forget about all these things now. We have done enough with this expression, and we are losing the physics out of it. So let us erase this. So you can write this Fs in the neater form. I write the same expression here. This k half rho v square, right? And then it is A plus Ch delta t into delta t, tab, minus dCm by dCl free into Ch delta by Cm delta into Cl. This further I can write as Fs equal to k half rho v square A plus Ch delta t into delta t minus k W by S Ch delta by Cm delta into dCm by dCl free. What has happened? What is the difference between these two expressions? You see, A plus Ch delta t into k half rho v square, fine. So again, k half rho v square has to multiply with this term if I want to take it out. But here, the Cl was sitting here, so Cl I can write as 2 W by S by half rho v square. As simple as that, right? Put that Cl here, multiply with this term, you will get this term. That is k W by S, Ch delta by Cm delta, dCm by dCl free. So this is, after a lot of struggle, we got a neater expression. Okay? What does it tell you? See, all those expressions, alpha t, epsilon naught, what not. Finally, what you are seeing here is very surprising, that a stick force primarily depends upon this term, v square term, it goes here. But here, if you see, nowhere speed is there. This is only dependent upon the stick free status of the airplane. And what are the hinge moment characteristics? What is the wing loading? But nowhere v is there. Could you see? And here v is there with v square. That's not, isn't it very interesting? So we'll try to exploit this. What does this mean? So then, now, if you see dFs by dV, will be k rho v A plus Ch delta t into delta t. You see another big expression we are getting. The dFs by dV in general, it has nothing to do with dCm by dCl free. This is given by this, and you could see from here that the second term has no influence on dFs by dV. But try to argue why it is happening like that. It is happening because, please understand, dCm by dCl free is relevant about trim. All this stability, we are talking about the slope at trim. So, if you want to really bring this dCm by dCl free in dFs by dV or in the stick force gradient at V trim, then you will find dCm and dCl free will again reappear. Okay? Let us do that. Before we do that, we will also try to give a more insight to this expression, Fs. What is happening? This V and this is Fs. There is a constant term which is Ch delta T, Cm delta, dCm by dCl free, W by S, wing loading, and K. This is a constant term which is independent of V. What is the sign of dCm by dCl free? It is minus. This is minus, this is minus. So minus minus plus, this is minus. And you know, K is also minus. Remember the expression of K? If you see the expression of k, you will find there is a minus sign sitting there. So this is also minus, so minus, minus, plus, and minus. So this is a constant force, Fs, constant will be there. And what is the sign of that contribution? This contribution is negative. So it is, as per a convention, it is a pull. I repeat here again, watch out for this term, second term. Okay, it is this. This is one, this is independent of V. Second thing what we are seeing, it depends upon, of course, wing loading. If I see the sign, this is minus, this cancels out, this is minus, and k is also minus. If you see the expression of k is minus, cancels out, and this minus sign is sitting here. So this whole contribution is negative. So the negative constant force will be there in this expression. And that is negative means a constant pull force will come. So what we will do, if I write on the top, this is pull, okay, which is negative. So you'll find a constant pull force because of stable CG, which comes from dCm by dCl free being negative. If it is unstable airplane, statically unstable, and dCm by dCl free was positive, then this sign would become positive, but that was should have been here for unstable CG. Let us focus about statically stable airplane. So this we know fine. Now what is happening? See the first term, this term. What is this term doing? This is k half rho v square a plus ch delta t into delta t. Assume that a is not that significant. And you could see that. Let me draw it, then I'll explain. Let me write this. If I, for time being, if I neglect this contribution of A, which is very small, then you could see that if I put delta t positive, that is, I'll put the tab like this, if delta t is positive, okay? Tab is positive. Then what is happening? I know Ch delta t is negative and this is positive. Positive means nose tab up. What is the meaning of that? That is, this is the nose of the tab, it is up. So, you know, this is, as far as we understand, the tab has gone down like this. Okay? So the nose has gone up. If it is the trailing edge, and the nose is up position, that is delta t positive, which is same as elevated delta E positive, same convention. So if delta t is positive, this is negative, that gives me a negative, and k is negative here, so that will give me a Fs positive. Please see this. Fs because of tab will be how much? K half rho v square, right, into Ch delta t into delta t. If I put this is as a positive, which is nose up, in a sense, this is what you call nose tab up, delta t positive. So this is positive, this man is negative, and k is also negative, we know by definition. So what is happening? Positive, positive, positive into negative. Okay, so negative. So negative into negative, positive. So Fs I am getting positive. So this will give a push force by convention. This is clear? This is positive, this is negative, and this is also negative. So total sign become positive. So it will, this term, as V is increasing, you will find it will contribute towards opposite of a pull force, right? So that is why if I go on giving delta t positive, and as the V is increasing, or a particular delta t you can set, as V increases, see this contribution, more of positive it gives, and finally it nullifies here. And if you see this difference is, I write it force due to tab, right? This element, right? Okay, which is you could see very clearly if I put tab in this configuration, then that is giving a force, stick force Fs, which is positive, right? And this stability term was giving a negative force, which was like a pull force. So there will be a point where net Fs will become 0. So this is the point where how you can ensure that Fs goes to 0 through tab. This is very clear. That is how I was telling you can bring equilibrium using a tab by proper tab setting, if you understand this. Now, we have also need to discuss about why DCM by DCL free was not explicitly seen. Now we will be focusing our attention, we will focus attention to trim. It's very important because we need to know what is the force gradient I need to apply, and that is I have to apply at the trim. Okay? So let's assume that suppose it is let's say it is required to ensure Fs equal to 0 using a tab. We have seen how can you make Fs 0 using a tab. That is, if I expand this statement, I would say, assume that trim is always deflected in such a fashion that automatically Fs equal to 0 comes, right? The trim tab takes care of it, and we say that airplane is trimmed using that tab. Okay, clear? If I do that, I need to know what is that Ch delta T to delta T contribution by tab to ensure Fs equal to 0. That you can easily find out because I know Fs equal to k half rho v square into A plus Ch delta T into delta T minus k W by S Ch delta by Cm delta into dCm by dCl free. The question is, what is Ch delta T so that F is equal to 0? As we have been discussing here, it is assumed that the tab is rolled appropriately all the time to ensure it is at trim, that is F is equal to 0. And corresponding to F is 0 will be the V trim. Okay? With that, we are now trying to find out what will be its contribution. As you understand, we want to deflect the tab such that it is a trim is F is equal to 0. So I put 0 here, and I put this expression equate to this. So what we are looking for? We are looking for what is this contribution of Ch delta T into delta T, that is contribution from the tab, so that it ensures that F is equal to 0, right? It has the trim. If I now do that, I have to put F is equal to 0 and this expression. So from this we will get, see yourself that we will get an expression Ch delta T into delta T equal to 2 W by S by rho V trim square Ch delta by Cm delta into dCm by dCl free minus A. Okay, you could see here this is equal to 0. So I take this here and then divide by half rho V square. All this thing you will get. Okay. Please understand, when I am putting F is equal to 0, I am assuming that tab is rolled to ensure that it is at a trim. That means then V will be equal to V trim. Right? Okay? And that is why you find here this V trim. Clear? No issues? Okay. Now we see. So what will be Fs now? Fs will be, Fs expression you know, k half rho v square into A plus Ch delta t into delta t minus k w by s Ch delta by Cm delta into dCm by dCl free. Okay? This already you have derived. What I have to put? I have to only put the Ch delta t into delta t by this expression. Clear? This will come here. And then you can easily write Fs equal to k w by s Ch delta by Cm delta into dCm by dCl free V square by V trim square minus 1. Fantastic expression. What you have done? Ch delta t into delta t, you have just substituted this expression. How you got this? Because we made an assumption that the tab is rolled automatically so that Fs is 0, so the trim is achieved. So we found out how much tab is required for different V trim, for different wing loading. That we put in the general expression. So we got this expression. Okay. Now, you see, if we differentiate, you will get dFs by dV at V trim. That is, I'll evaluate this V equal to V trim. Then I'll get it 2k W by S Ch delta by Cm delta into dCm by dCl free now have a closer look. Here, one thing I am seeing dFs by dV, now you see dCm by dCl free is coming, right? And please understand, fundamentally, we are calculating dFs by dV at V trim, at equilibrium. So dCm by dCl immediately appeared here, which is correct, slope, right? If you see here, this is the sign, it's negative, this is negative, this is negative, okay? So this become positive, is negative here, k is negative. So actually, if it's d phase by dV, by this expression, it becomes greater than 0. Is it clear? Please understand that k is minus, this is minus, this is minus, and this is minus, this is this. Now, I will plot this in a different manner. That is where we should be careful. We have taken push force as positive and pull as negative. But we will be plotting it now differently. We will put pull here, that is negative, and push here. So naturally, we will find dFs by dV will become now negative. Okay, this is clear, and this is the V trim. Please note down, this is pull has been put in the y-axis, push below this x-axis, right? So naturally, the slope will be different. So this is the dFs by dV when you're plotting like this, pull as negative, push as positive here, right? So what does it say? It says, this is Fs. Like you had delta E versus CL trim, graph like this. What that graph was used? Through stick fixed stability concept, that if I want to fly at this CL, this was a delta E required, right? Now what is to be inferred from this graph? That if I am flying at this V trim, if I want to go to this V trim too, I have to apply what type of force? Push force for unaccelerated flight. What is the meaning? That if I am flying at say 100 meters per second, if I go to 120 meters per second, so it says you have to apply push force. How much push force? It will be dictated by the scale. So it is consistent. I want to increase, so I am giving push. If I want to reduce the speed, then I have to give a pull force, negative. Okay, and this is positive, push. Clear? Also it tells you that if you push the stick and take V trim to this point, and now withdraw the stick, it's a reversible control. So again, the speed will come to this V-trim. Similar true is here. One thing you can understand, if you could see the gradient of dfs by dv for 1 is more than the 2, right? If it is large gradient, one thing is ensured that if the pilot lifts the stick, it will always try to oppose any change from that fs equal to 0. So you can fly safely. Right? You can fly in a relaxed manner. If this gradient is too low, then for small disturbance, pilot has to control it, right? But if it is if gradient is high, then it tells you it requires larger dfs by dv to go from one v to another v. So in a way, it will be resisting, right? So pilot can fly at ease. This is also extremely important. Okay. Okay, I will end it here, and I know there are a lot of expressions have come. In one of our Mann Ki Baat session, we will take up one of the topic and again revisit. Okay.